So we are doing two simplifications here. One is, first of all, we are considering one dimension. The second thing that we are looking at, steady. I would like to point out that for what we are trying to do here, we don't need to make these assumptions. Okay, in other words, the final result that we are going to get should be valid for a three-dimensional unsteady flow as well. Okay, this is just to keep things simple in what we are going to do now. What are you going to do now? Recall in what we did up until now, we wrote up the equations of conservation for combustion and found that we had 5n plus 6 equations to solve, and n was like 20, 40, whatever, and so correspondingly we had like a large number of equations to deal with. So the question is it possible for us to A, reduce the number of equations, and B, is it possible for us to decouple some of the equations so that it is sufficient for us to solve only one set of equations for doing something, another set of equations for doing something else, and these are not exactly coupled with each other, except that maybe we get solutions from one and plug into the other, and that is it. So that means, like, as far as the second is concerned, the first solution is given to it, we do not have to solve it coupled with it, and as far as the first is concerned, we did not have to worry about the second set of equations at all completely and just go ahead and solve for this. So this is what is meant by decoupling sets of equations, and we will try to understand what this idea leads to in concrete terms, or in other words what decouples from what and so on at the end of what we are trying to do. But as I said earlier, from now on all we are going to do is to completely go in the direction of simplifying things, right, and then deal with a few simplified situations from now on. So one of this is not the way of looking at simplification. This is the simplification here on one dimension and steady is to just make what we are going to do now simple, but at the end of it we are going to come up with some simplification that is valid for multi-dimensional, that is three-dimensional steady flows, unsteady flows as well. So let us now look at the simplified situation. If you now have the overall continuity equation, can be integrated to give. So what the overall continuity equation we had was dou rho by dou t plus divergence of rho v vector is equal to 0. So steady means you do not have a dou rho by dou t, 1D means we have a d by dx of rho u, okay, and if that is equal to 0 we can integrate that to get rho u is equal to constant, right. So okay, the momentum equation for 1D steady flow, and let us also neglect body forces. Now neglecting body forces mean whenever we are actually making these kinds of assumptions that let us neglect this or assume it to be negligible, those kinds of things, we have to question it. Is it okay to neglect body forces? Okay. So in combustion, one of the problems that we will find about this is the body force pretty much is the one that is actually giving rise to the shape of the flame as we know it. So if you now light up a candle, okay, like for example you go for a candlelight dinner party with your date, and then you are trying to enjoy the moment, unfortunately then you start remembering about combustion because you have this flame, and then the entire evening is shattered, right. So what are you looking there? You are now looking for a flame that is kind of elongated vertically, okay, assuming that your date is happening in a gravitational field and you are not really going in free space. So if you were in free space then or a zero gravity environment, you now should actually look for like a bulb shaped flame, whereas if you now are in a gravitational field you have a buoyancy force that is actually trying to push this flame in an elongated fashion. So the question is it okay? Obviously if you neglected body forces you are not going to get flame shapes that look like anything that we are used to around here on this planet, right? Well, the answer is maybe all that shape is not really important, okay. For the purpose of burning the candle, it's the heat that is actually being released closest to the candle surface that is really what matters for melting the wax and getting the liquid to go through the capillary pores of the wick and then vaporizing to feed to the flame. So we didn't have to really worry about the shape of the outer shape of the flame far away from the wax surface, the candle surface, right. So many times what you will find is it is okay to neglect the body force, not a big problem there. So if you now did that, then you get your momentum equation, which looked pretty ominous previously. It's now going to look like u du by dx equals 1 over rho d by dx of p plus 2 over 3 mu du over dx minus 2 mu du over dx. Well, as we can see from what we have done even in the continued equation, there is only one direction that we are looking at, the x direction, and we are only looking at one component of velocity that assuming it to survive, which is the x component of velocity, and that's called u, okay. And since you're looking at only one direction, it's sufficient for us to actually replace partial derivatives by ordinary derivatives with respect to x. So you have a u du by dx, this is coming from the convective term, is equal to minus 1 over rho d by dx of p, that's the pressure gradient term, and then this is the bulk viscosity term, and this is the viscous shear stress term, okay. So these are the terms that survive. The unsteady term dropped out because we are looking at a steady flow. Pretty much all of the terms are around. Of course the body force has been neglected, okay. So this could now be written as, if you now write this, what would I like to do if it's possible for me to write the whole thing as a derivative. What did we get over here? We had a divergence of rho v is equal to 0 for the vector form. In 1D we had a d by dx of rho u is equal to 0. So similarly if I can actually get something like a d by dx of something equal to 0, I should now be able to say that something as a constant. That's very easy for me to integrate. It becomes like a exact integral for me to evaluate. Therefore so we can now write this as let's say d by dx of rho u, rho u squared, okay, equal to minus d by dx of p plus 2 by 3 mu du over dx minus 2 mu du over dx. How did I get this? Well, first of all I could take this rho to this side, okay, and notice that rho u is equal to constant. So if since rho u is equal to constant, I could actually take it inside the derivative, alright, and there is a reason why I got a d by dx of rho u squared, okay. So what that means is I had a d by dx of this equal to minus d by dx of that, which means I can combine both and have 1 d by dx, right. So if I now put everything together and have a d by dx equal to 0, then whatever is inside the d by dx should be equal to constant, which is now in our case rho u squared plus p minus 4 by 3 mu du by dx equal to a constant. Okay, we are now beginning to see things that we are somewhat familiar with from, let's say, gas dynamics. All right. Previously in gas dynamics you would have done typically inviscid flows where you had a P plus rho u squared is equal to a constant for compressible flows. Okay, in fact rho u is equal to a constant actually comes for compressible flows, right. Otherwise you would have had something like a of course in quasi one dimensional situation you would have a rho u a is equal to constant. This is just one dimensional, not even quasi one dimensional, so you don't worry about an area, you only worry about a mass flux, you don't worry about a mass flow rate. Okay, but you have to take into account the variation of rho with velocity. That means rho is varying, it is a compressible flow. Okay, and that is the reason why you have rho u squared plus p. Okay, but that is not equal to constant like what you had seen for inviscid flows because we are still considering viscosity, so you have this extra term that comes into picture due to viscous effect. Okay, and that is actually putting the bulk viscosity and the viscous shear stress terms together, you get a minus 4 by 3 mu du by dx. So previously we did not have this term, we now have this. If you were to look at like an incompressible flow, you need to have a half rho u squared plus p is equal to a constant. For Bernoulli's equation the half did not come because rho was varying here. Okay, previously if you had only a incompressible flow the rho would not vary, then you would have a ua is equal to a constant for a quasi 1D situation. That is what you are familiar with for a Bernoulli's equation approach there. So all these things are not very different from what we have done before, maybe with the exception of having this extra term. Long later when we are trying to do detonation we will try to revisit the situation and then see how the flow transitions from its initial conditions to what is called as the Chapman-Jouguet detonation later on through many states that correspond to this. Okay, so what we will want to do now is let us say we can write this as rho u squared over p plus 1 minus 4 over 3 mu over p du over dx divided by equal to constant over p. Why am I doing this? The answer is I want to have a 1 in this so that I can compare the other terms relative to that. Okay, it is sort of like always looking at making a comparison with 100%. So how many marks is this going to score with respect to 100%? How many marks is this going to score with respect to 100%? Okay, 100. So 1 essentially is like a benchmark for us. So why did we actually choose pressure to be the one in the denominator and make the pressure term equal to 1? The answer is we are now going to actually examine how this is going to compare with 1 and see that under low Mach number conditions this is very small and this is also very small. Alright, so all small with respect to what? Small in comparison to what? With respect to 1. Alright, so that is what we are trying to look for. So P, note that P over rho equal to RT A squared equals gamma RT, where A is the speed of sound. So this implies that P over rho equals A squared over gamma, or you could have said A squared is equal to gamma P by rho, right, which is something that we know. All this is for a perfect gas, of course. Therefore then if you now try to plug P by rho would now be in the denominator in this term, right. So u squared divided by P by rho is what we have for this term, and that would be simply u squared divided by A squared divided by gamma, which is basically gamma m squared, right. So u squared over P by rho is equal to gamma m squared. Okay, keep this with you. Let's look at the third term over there. The second term of course is 1. So let's look at the third term. From kinetic theory, I told you that we have to have something for mu, and mu is a transport property, and transport properties can be evaluated only if you go down to molecular level. That means we have to go down to kinetic theory. We can't get it from continuum effect. Within the continuum framework you simply have like a law that states that shear stress is directly proportional to velocity gradient, and the constant of proportionality is something called viscosity. Okay, that's like a law that we just observe in the continuum world without knowing why. If you want to know why, you have to get down to the molecular level, and then you will be able to find out what viscosity actually means in terms of molecular level fluid motion. Alright, so if you want to know how the mu depends on things like pressure and density and temperature and all those things, typically you can try to relate it to two thermodynamic properties, and then there is a dependence. Okay, so what you are looking for is mainly like a dependence rather than the exact expression, because we are looking at an order of magnitude approach. Okay, relative to unity, we are trying to see how this fares relative to unity. So mu can be written as rho a lambda, where of course a continues to be the speed of sound, now how did you get the speed of sound to come in for the viscosity? That's not very surprising, because if you want to actually try to find out what is speed of sound, you have to get down to the molecular level as well, because it's a molecular level phenomena that is actually propagating sound. Alright, so all these things are related there. Lambda is the mean free path. What's mean free path? Mean free path is basically the average distance between average distance covered by a molecule between successive collisions. Alright, so now what we have to look for is du over dx. That means we have to look at an order of magnitude of what that derivative is going to look like. So if delta u is of the order of u, that means the changes in velocity are of the same order as the velocity itself, as in this is not to say that the changes are large, it is essentially saying that the changes are actually measured as appreciable fractions of this of the velocity. So for example, if the velocity is let us say 10 meters per second, and when you are now looking at du by dx, in fact we should now also start looking at what's x going to vary like. So delta x, let's suppose it goes as L. L is like a characteristic length, characteristic dimension of the problem. So we come across these kinds of things when you do things like flow past a sphere or something, or flow through a pipe and so on. So where we have characteristic dimensions, right, like the sphere diameter or the cylinder diameter or the pipe diameter, all these things, these are like characteristic dimensions. So if you now have flow through a pipe and the pipe is about let us say 50 millimeters large, then you would try to actually measure the or take divisions like go 1 mm apart or something of that sort, right. So what we are talking about as x is, it's going to be a fraction of the characteristic dimension, or in other words we are not going to take delta x to be very much smaller when compared to the characteristic dimension. Okay, it's going to be of the same order. So if you now have like 50 mm, we are going to go in steps of like 1 mm, which is of the order of about 0.02. Okay, so that is still like in terms of what the characteristic dimensions are. If for this kind of change in x, okay, of course x is in the axial direction in this particular case. So if you want to now look at what happens in this direction, you could even do much larger than 0.1 mm. You could even do things like, let's look at what happens every 5 centimeter, 5 mm. okay. So delta x now simply becomes like 0.1 which is or 0.2, so you can take larger steps, and if velocity is changing if it's going at 10 meters per second and we are changing by 1 meter per second over a let's say 10 mm difference, then these are all du over dx is of the order of u by L. That's essentially what you're talking about, what you're saying, okay. So then 4/3 mu over p du by dx now goes as let's forget about 4/3. 4/3 is not very different from 1, okay. Now this is some new math, yeah? So where we kind of cheat on these like, of course when you're in your 4th standard or something like that, you really start mugging about these decimal places and all that stuff, and then as you grow older and older you become like a lot more scrupulous about like 8 decimal places accuracy and so on, and then finally you come to graduate school and we say like 1.33 is the same as 1, forget about these 2 decimal places and all. Oh, come on, is this why we studied so hard? Okay, that's exactly what is meant by order of magnitude. Huh? So let's not worry about the 4/3. So we now say, oh, if you want to worry about it, keep it, don't worry about keeping it or leaving it. So then mu goes as rho a lambda, then keep it as p here, and as I just try to belabor the point, delta u over delta x is like u over L, right, and we should now know how to rearrange this. You can get the rho down here, so as p by rho, and then we now notice that p by rho is a squared by gamma, so I can now plug in a squared by gamma over here without the rho there, and then the a gets cancelled, okay, the gamma goes to the top, and then you have a over here at the bottom, there is no a at the top anymore, but u and a get together to make an m, and lambda and L get together to make what? When was the last time we thought about the mean free path? Huh? The Knudsen number, right? So the mean free path relative to the characteristic dimensions of your problem, okay, is something that you come across the first time when you do fluid mechanics, typically when you're convinced, or rather brainwashed into thinking that we will have a continuum approach that can be justified by looking at something called a Knudsen number, which is very small for typical situations like the kind of flow that we have in this room, okay, atmospheric pressure, room temperature, the air is so densely packed when compared to the mean free path. Let's say you're now looking at flow past this table, okay, that's like billions of mean free paths there, okay. So the Knudsen number, so this together gives you the Knudsen number, and as I said, you can get a gamma m from the other part. So this is actually going to give you a gamma m Knudsen, right, if you want me to write what this is, that is Knudsen number Kn, right, and for typical continuum applications Kn is very small, okay, Kn is like 0.001, 0.0001, whatever, it's a very small number, 10 to the minus 3, okay, whatever. So now Kn is very small for continuum flows, right. Then the question that you ask is, wait a minute, we are doing combustion, is combustion continuum flows? Didn't we start talking about like molecules colliding with each other and reacting and then you even talked about like the molecules need to be exactly oriented so that you have like effective collisions, and then you will have the chemical reactions for some atoms on some parts of the molecule with some other atoms in some other parts of the molecule and all that stuff. Weren't we talking about all those things at the molecular level? Why are we now suddenly saying continuum? Yeah, I mean continuum doesn't mean that there aren't molecules, okay. So the fact that we have to actually use the law of mass action and the Arrhenius law is because we are actually looking for a continuum representation of those chemical reactions. The fact that we are able to actually define a concentration of a species at a particular point which actually contains billions of molecules of all the species at that point, okay, means that we are actually dealing with continuum. So even though the chemical reactions are happening at the molecular level, it is happening at a point where you are looking at millions or billions of molecules of lots of species at that point, with each of them being able to be represented by a concentration at that point. Concentration means you need to have like certain mass for that given volume of that little point, or a certain number of moles of that for a given volume at the particular point, okay. So you are now saying that that point has a little volume and then there is a mass associated with it and all those things, and the point that we are talking about is like a mathematical point in space where your chemical reactions are happening. Now it is not like it is happening in this room or things are happening the size of this room. You have to start now imagining like a flame that you encounter, okay. Let us say for example if you have a Bunsen burner, you now have a flame, you are now thinking about a flame that is like a millimeter thick or even smaller, okay, and then you now should be able to pick a point within that flame, and at that particular point you now have all these chemical species with their concentrations and so on, alright. So it is a continuum flow, that is not a problem at all, and therefore, so finally what do we have for low Mach number? For low Mach number flow, how low? How low is low? 0.3? 0.3 is low? No, 0.3 is like this magical number that we have in our minds about when the flow is still incompressible or just become, nah, don't worry about all those things, right. What we are talking about is Mach numbers that are even lower, right. They are like about 0.1 or less, maybe 0.01 or 0.001, okay. We are typically talking about hot flows here. The temperature is large, so the speed of sound is very large, okay. Therefore, or I should say the other way, that the temperature is very large, therefore the speed of sound is large because it goes the square root of temperature. So you have a large speed of sound, so even for a moderate velocity, okay, your Mach numbers are fairly small. So if you were to think about a Mach number of about 0.1, I think I have made this point before, if you now think about a Mach number of 0.1 that is happening in like a, let us say a gas turbine combustor, okay, and the temperatures there are in the reaction zone are of the order of like 2500 Kelvin, therefore the speed of sound is of the order of 1000 meters per second, then we are still talking about velocities that are about 100 meters per second. That is like, this pretty, the flow is fast but the Mach number is low, okay. So we are now talking about low Mach numbers less than 0.1, okay. And that is not a magic number, it is not like a God given number. If it is like 0.11, then don't start shivering, huh. Which is like 0.09, don't feel like a huge relief or something of that sort, nothing of that sort. It's very low, that's what you're saying, it's quite low when compared to 1. And then what do we have? We now say this term which is now beginning to look like this, if m were like 0.1, m squared is like 0.01, okay, and Knudsen is already like 0.01 or less, and m is again 0.1, so this term is going to be much smaller, right. So then both rho u squared over p comma 4 over 3 mu over p du over dx are much smaller when compared to 1. That means in this equation we should now try to get rid of this, and then we are left with only 1. Okay, we got rid of these because they were actually very small when compared to 1. So if you now get rid of these, we have to keep the 1. Okay, so we now keep 1, and then what do we have on the right hand side? We now say 1 is of the order of constant divided by pressure. That is to simply say that pressure is approximately a constant. Okay, so this simply means that P is approximately a constant. So what have we done? We have practically shattered the momentum equation down to a P equal to constant equation. We started out with a momentum equation and then just systematically dismantle the momentum empire, if you will, okay, to get it down to a teeny weeny equation that is like just P is approximately equal to a constant. Is that okay? Does it make sense? So you light up a Bunsen flame. Do you feel like a pressure around? Okay, so you go to your kitchen gas stove and then light up the gas stove. Do you feel like a pressure around? You don't really get like a lot of pressure around. Okay, it is just approximately constant atmospheric pressure around there. That's all right, but what about a gas turbine? That's really going at very high speeds. I'm pretty sure there must be a lot of pressure. Yeah, the pressure is high, but it is approximately a constant. Right? So we are talking about fairly low subsonic combustion happening roughly at a constant pressure. All right. As a matter of fact, whenever we were looking at these kinds of things like neglecting body forces, or when you're now saying let's say continuum, and then we're now looking for low Mach numbers, we don't necessarily have to think combustion, right? If you now had a non-reacting single species flow, okay, like ordinary fluid mechanics, and we now say let's not worry about body forces, that's okay. In fact, in combustion that we had to worry about body forces and then neglect it, right? And then it's continuum flow, sure, so Knudsen number is quite small, and we are thinking about low Mach number fluid mechanics there anyway. So all these assumptions that we are making along the way are satisfied for a normal fluid mechanics flow, and then we should now be able to reduce our momentum equation down to P is equal to a constant. Why are we stuck with a momentum equation that we are not able to solve for 300 years when it should just be said as P is equal to a constant? Are we getting any information here? The answer is, so let me think about it. You just have a piece of pipe, let's say a small piece of pipe, and then you now blow through this pipe, okay, and then of course you can play with this, and you can put your hand on the other side and then feel the cool air that's coming out because you're blowing and so on. Of course you don't really get a lot of pressure out there, so it's all approximately atmospheric pressure. That's really the key. How much did you blow with, right? The answer is a little bit more than the atmospheric pressure, therefore you could actually get the flow out to atmospheric pressure. So the delta P that we are talking about there is very, very small, so that this flow field is approximately at a constant pressure, but there was a small pressure gradient that was required to drive the flow. This is what we are talking about for this kind of low Mach number flows, okay. So this is not to say that the pressure gradient doesn't exist, it's quite small, and that is good enough to actually drive a low Mach number flow. As a matter of fact, in a gas turbine with all the complicated machinery, like you have these swirlers and you have a flare and a sudden expansion and all these things, you are expected not to have a pressure drop of not more than 5%. If you have a gas turbine that's having a pressure drop of more than 5%, it's a bad design, okay, you try to get it up to 95% pressure recovery, alright. So you are not looking at a very huge change in the pressure at all for all this big flow that we are talking about, okay. So this for us does not mean that the momentum equation is gone. The momentum equation is still required for you to get the flow field, except the momentum equation now gets decoupled from the species equation and the energy equation. This is what it really means, okay. That means we are starting out with the overall continuity and the momentum together. They constitute what is called as the flow problem. If you now had the flow solved for, that is basically cold flow, so you are given a very complicated geometry with all this let us say a pre-diffuser, a dump diffuser which is very highly curved, and then you have the swirler and atomizer that is coming through, and then you have these liner pores, and then you have flare, and then all these secondary holes, and then the dilution holes, and then you have this liner flow, and then there is a casing around, and you have this combustion going on inside. All these complicated things, do not worry about all that stuff, just take this geometry and then do a cold flow, okay. Work out the flow field in this. That means you now take your incompressible equation set for fluid mechanics, namely the continuity equation and the momentum equation, solve for the flow field, okay. You get your velocities. These velocities now can be plugged in your species equation and your energy equation. That means we now want to worry about the combustion problem as constituted by only the species equation and the energy equation. In other words, we now say we want to split the set of equations that we have had into a flow problem that you solve independent of the combustion problem, and you solve this flow problem, get the flow field, plug it into the combustion problem. So what is the flow problem? Overall continuity and momentum, okay. What is the combustion problem? Species conservation and energy. These are now decoupled, and there is only one way interaction, which is you solve the flow problem independent of the combustion problem, get your velocity and plug it in the species. Where do you need this? In the convective terms for the species mass fraction convection and the enthalpy convection in the energy equation. So you need the flow, the mixture velocity, right. So you now plug this in there, right, and then this is your combustion problem. You just solve this set of equations for a given flow field, okay. Now many times the combustion people do not have time for the fluid mechanics people, they get just assume a flow field. Okay, I mean if you are really strict enough, you would probably assume a flow field that satisfies overall continuity and momentum, and many times in simplified problems a assumed flow field that satisfies overall continuity and momentum is simply a uniform flow, okay. So you just assume a uniform flow that naturally satisfies overall continuity and momentum, and then plug that into your species conservation and energy conservation, okay. And that also simplifies your species and energy conservation, because you are now looking at a V dot del yi and V dot del t kind of terms, right. And then so if you now look at V dot del, if you have only one dimensional velocity, that means velocity in only one direction, it simply reduces to u du y, u dou y by dou yi by dou x and u dou t by dou x. You do not have a v term at all, okay. So the lateral convection term gets absent, so you do not have to worry about it, okay. So this simply means that we do not solve the overall continuity and momentum equations as part of the combustion problem, right, but obtain the flow field by solving them and use it as prescribed in the combustion problem, right. So what is meant by the flow problem then is overall continuity plus momentum equation, right. And then we have the combustion problem, which is the species conservation and energy equation. So when you now say this arrow, that means flow field prescribed. So many times that means we do not even care to solve the momentum equation or the flow problem, you just take a flow field that is prescribed as far as the combustion problem is concerned, okay. Now I do not know how many of you are really thinking about this as well as we should. What do you mean by saying I prescribe the flow field and then the convection of species and enthalpy is going to happen as prescribed, right? The question that you have to ask is, doesn't this affect the flow field back? Shouldn't we have an arrow backwards? Well, I would like to say two things here. One, if you were to have an arrow backwards, still be happy that I could draw these boxes separately and identify a flow problem different from the combustion problem, and then have a interaction that is explicitly understood between these two, as opposed to putting one big box for all the equations and saying that's it, you have to solve all of them all the time, okay. I am still thinking about decoupling these problems. That means my solution procedure for this may be different from the solution procedure for this. This is the one that is containing all these bad terms like the chemical reaction terms and all those things. So I may have to have a solution procedure that is different for this than this, right. So it still makes sense for me to think about these as two distinct problems even if they have a two-way interaction. But what I have now talked about is only one-way interaction, okay. But shouldn't you really have a two-way interaction? That means shouldn't the combustion actually affect the flow field? Why would it? Yeah, of course it will. If you now think about a candle flame, right. So now let us light up a candle, and then assuming that we are thick skinned, which I am, okay. So I now take my finger very close to the flame, but somewhere near the bottom. Let us suppose this is the flame, okay. It's a big, it's a what do you call, exaggerated view here, right. The flame isn't so big, but I now take my flame somewhere here, okay. Of course I am beginning to feel the heat, alright, but I don't really sense a draft, I don't see any, like I don't sense a flow, okay. But when I now try to take my hand somewhere there, do I sense something? You now see a flow, you have a flow. Of course you might claim, yeah, that's because of the buoyancy, or the hot gases are rising up, alright. I can claim, well, if I were to actually go into free space or in zero gravity, I should now have a flow that is set up radially outward, okay, instead of going up, because we are not in the gravitational field, alright, but still I am going to have a flow, which is not the same as having more like still air at the bottom, okay. That is to say, if you now have a flow that is going through a flame for the reactants, okay, the density is low, sorry, the temperature is low, so the density is high, okay, but then when it now gets past the flame and it becomes products, the temperature is now high, so the density of this for more or less constant pressure, right, is now going to be low. So what does it mean for a low density as far as the velocity is concerned? If the rho u is equal to constant, the velocity is now going to go up. So sure enough, if you now were to think about like a Bunsen flame, right, you now have a cold flow that's coming in, this is like a blue flame, alright, but then the flow actually enlarges and goes up like that faster than it came in into this flame. So the density effect on temperature, sorry, the opposite, the temperature effect on density has the effect of dilating the flow once the flow goes through the flame, which in turn means that obviously the flame affects the flow, or the combustion problem affects the flow problem through the density depending upon temperature, okay. So you do have an effect, okay. This is because rho goes as 1 over T. I say 1 over T because we still assume or suppose that P is approximately a constant, right. P equals rho RT, P is more or less constant, therefore rho should actually decrease just as well as the temperature increases. So to give you an idea of what these numbers are, if you now think about a reactant that is entering a flame zone or combustion zone at, like, say 300 K, alright, and then it gets out there at, let's say, something that is divisible by 3 to make our life simpler, 2400 K, okay, that's more like it, okay. Of course you could have taken 2100 K or 3000, alright, but we are now talking about a difference, a ratio of about 8, anywhere between 7 to 8 to 9 something, right. So we are now looking at a ratio of about 8 times jump in temperature for typical hydrocarbons, and therefore the density also should actually decrease so much more, and the velocity then increases so much more, right. So but the Mach number doesn't change a whole lot, so the velocity increases, but because the temperature came down, so the temperature got up, therefore the Mach number came down, okay. So that's not a problem, you're still going to have like a P approximately equal to constant, but you now have a high velocity there. So it is possible for us to actually take this into account and then go back and then alter the flow and then prescribe a new velocity field into the combustion problem, find out how the combustion changes the temperature field and then therefore the density field and therefore the flow field and so on, but still this means we can actually decouple the two problems and solve them with different strategies, okay, but take into account this coupling.